Okay, welcome. So today we're going to be jumping into the next topic that's going to be simple harmonic motion. Going to try and give you a sense of sort of the relevant quantities to pay attention to in simple harmonic motion, a couple of the simple systems, and then how they connect to some of the other ideas we've discussed. Okay, so go ahead and share the notes and we'll get going. All right. So starting off with simple harmonic motion, let's just give a definition. So simple harmonic motion. And I'm just going to give a working definition for the moment. I'll also give an abbreviation. You'll see me use this occasionally throughout the topic. But basically what simple harmonic motion is, this is just the simplest form of, and I'll put this in quotes, back and forth motion, or back and forth type motion. Type motion. Okay, so that's what we mean when we're talking about simple harmonic motion. Now, when it comes to, so another term I'm going to introduce just so we can see kind of what's going on here is a simple harmonic oscillator. Now, a simple harmonic oscillator, I'll basically just say that this is an object, or in general, it's more of a system that undergoes simple harmonic motion. That undergoes SHM. Okay. So it's worth distinguishing these concepts because the simple harmonic motion is sort of the motion broken down to its simplest aspect. But you can have a simple harmonic oscillator in a system that's doing other things. Okay. So an example of this would be, it turns out that the strength of the chemical bonds between atoms in molecules, it actually approximates a simple harmonic it approximates a spring force pretty well. And a spring force is one of the things that generates a simple harmonic motion. So what we do is we treat these atoms like they're, if there's just two of them, like in an oxygen molecule, we treat them as if they're a simple harmonic oscillator. But that simple harmonic oscillator is doing other things. Okay, so it has its own speed, it has its own spin. All these things are going on with it. So a simple harmonic oscillator is just it's a system that can undergo simple harmonic motion, but may also do other things. That's the main idea. And again, the simple harmonic oscillators are, that is primarily how we analyze the atomic and molecular motion of different chemical compounds. So understanding what those are actually doing, it's actually quite helpful to understand the simple harmonic oscillator in these terms. Okay. So the two systems I'm gonna talk about, the two systems the book talks about are as follows. These are the two just kind of basic, simple systems that we will analyze to, or we would analyze to kind of understand simple harmonic motion. We're not going to be looking at that too much because it, well, because we really just don't have time to analyze these systems, but we'll go into some of it. So first one is a pendulum. And the second one is a mass on a spring. Okay. So a pendulum, just do a quick little diagram of a pendulum. So we talked about this a bit with the ballistic pendulum, but basically a pendulum is just a something that's suspended from a string, or maybe even a rigid arm going back and forth. You've seen a grandfather clock, you've seen a pendulum, basically. And like I said, we did use the ballistic pendulum in the lab as well. Now, a mass on a spring, I'll just indicate just kind of what I'm talking about here. And what we have is we have a mass, we have a spring constant K, this bottom surface is generally assumed to be frictionless. If we're actually demonstrating this, we tend to do it vertically. But then you have the spring force and the gravitational force. Now that's not that big a deal, but it's kind of easier to look at if it's frictionless. And basically what this thing is doing is it's going back and forth. So those are the two main systems that you have to deal with. Now the concepts of simple harmonic motion, they're not too bad. The first one I'll talk about is amplitude, and the symbol is going to be A. Now the units are open to depending on what kind of oscillation you're doing. So for amplitude of the mass on a spring, basically that would be the maximum displacement. So in that case, your units would be like in meters. But for a pendulum, a lot of times you do it in terms of angle. So you don't you in that case it would not have dimensions. So amplitude is going to be relevant. It's maximum displacement, and this also has connection to waves, which we'll be talking about here. But amplitude is maximum displacement of object undergoing SHM. Okay. All right. So next one to talk about T. This will be I'll do it. Try and maintain consistency, and we'll say what it is first, and then talk about it afterwards. So period. The symbol there is T, and this is the time of one SHM cycle. Okay. So just like period was the time when we are dealing with uniform circular motion, period was the time going around going through one cycle of the circle. Same thing with simple harmonic motion. It's just one cycle of the back and forth is basically what's going on. Now the units are going to be in units of time. So the SI unit would be seconds. Okay. And then there's frequency. Symbol will be a lowercase f, just like with AC circuits. And this is going to be the cycles per unit time of SHM. Okay. So the units are, so we'll define this. F is equal to 1 over T. The units are going to be 1 over seconds, or more commonly, this unit of 1 over seconds is the same thing as a hertz. So that's how we're going to use that. Now it is worth noting that the period is also equal to 1 over the frequency. So those two are related in that way. You could manipulate either one of those equations to find that. Okay, so to real quickly talk about why a mass on a spring does what it does, what I'm going to do is I'm going to draw, I think, a series of like 5 pictures. The first one, so 1, and this will be when it's, I'll spread this out to here. Okay, so basically what I want to do here is I also want to color code things. So we'll go with red. Right now, that would be the amplitude. Okay. Now, if that's the amplitude, then we've got a velocity of 0. So basically, this is as far as you stretch it. Now, it's worth noting that this time the force is going to be fairly large, not X, but force. And I'll try and make this a little bit bigger. I'll put it down here. We're going to have a large force, a spring force to the left in this case. Okay. Now, let's can I make this a little bit better? Just don't want the Okay, 1 second. I am going to Gonna pause the recording. Okay, and I'm back. Just had to figure out how to how to get my pens to not disappear while I'm doing this. Okay, so this is step one. Now, if we go to step two, basically what I want to do is I want to have the same sort of thing here, but this time the spring is not quite as, it's basically coming back towards the center. Okay, and what we have here is we basically have, we still have some delta x, but in this case, our delta x was equal to our amplitude. Our delta x is now smaller than our amplitude. Now we're also going to have some velocity going in this direction, and I'll make that just kind of a medium arrow, just for qualitative purposes. And the same thing, we still have a force in this direction, but the force is now going down. Why is it going down? Well, basically, it's because the spring isn't stretched as much. Okay, so basically, what is happening here is this spring is kind of exchanging some of the force for velocity. And we can think about this as an energy conversion. So over here we have U sub spring, and then our kinetic energy was equal to 0. And so we would say U sub spring max. Now U sub spring does not equal 0 here, and kinetic energy does not equal 0 here. Okay, so that's what's happening. What you have at step two is kind of a mixture. Okay, and this is like, we're not holding it, we released it. And again, it's worth putting that this is, I'll just indicate this is frictionless. Okay, if there's friction, then it won't be quite the same. But basically that's what's going on. Now we go to step three. What happens when the block gets back to the middle of where it was? Well, what we have here, try and just indicate that. Right here, we have delta x equals 0. Now, what we have is we have a large velocity here. Okay. Now, what we also have is that f is equal to 0. All right. And again, the whole reason here is because, again, this thing has moved back to its equilibrium position. So there's no more spring force. And so what we have now is we have our spring energy is equal to 0, but our kinetic energy is at its maximum. Okay. So we kind of talked about this a little bit, where we have energy converted to and from spring, to between spring and kinetic energy. That's basically what's going on here. Now, if we watch this into the next step, well, it's a little bit compressed. Okay, so what we have here, that's not quite right. Wanted the box to be a little bit bigger. So, all right, so what we have there now is we have some delta x. And again, it's not the maximum delta x. But what we have now is we have a medium force pushing this way, but we still have our velocity, but the force has now started to slow down our velocity. Okay, so again, the velocity has decreased. That's why the velocity is smaller. And so we now have some more spring energy. We're now back to not equal 0, but still some kinetic energy as well. So kinetic energy is also not equal to 0. Now, finally, in the fifth step, what we get to is the box, or the spring, is basically as compressed as it's going to get. Okay. And the idea here is that we have our V equals 0. We've got our delta x, and we have a large force in this direction. Okay, so basically what we've seen here is we've gone from having a force in one direction to having a force in the other direction. And we've actually gotten back to the point where our U sub spring, potential energy of the spring, is back up to a maximum, and our kinetic energy is now equal to 0 again, okay? And basically what simple harmonic motion means is that this is going to go back and forth. It's just going to keep doing this perpetually. Now, it won't keep doing this perpetually because we know that there will be friction, and when we have energy dissipated as friction, that energy becomes heat, and that is how we lose mechanical energy. Okay, so that's what's going on there. But assuming it was frictionless, this is what would be happening. And it turns out that even though you do lose some energy, if you bob the thing vertically, you get much closer to simple harmonic motion. Like it takes a while to damp the system. We'll talk about damped oscillators in a moment. But in any event, what I wanted to give you is I wanted to give you the period of this system. Your amplitude can be basically, say your amplitude can be anything, but the period of this system, to derive this, you need a little bit of calculus. But you can find the period using just this formula, square root of m over k. Now it's worth doing a unit analysis here. 2 pi has no units, but what we have here, so this will be units. The units of the numerator are kilograms. The units of the denominator are Newton per meter. If you remember, those were the units of the spring constant. Well, fleshing this out a bit more. Kilograms still in the numerator. We're gonna change that that Newton per meter. We're gonna change the newtons to kilogram, meters, and then per second squared, but we also still have that meter in the denominator. Okay, so some interesting things kind of happen here. This Newton per, this thing goes to there, and then the Newton became this thing right here. That's what a Newton is. But we do get some cancellations. These cancel, and it turns out the kilograms cancel. So what we end with is the square root of 1, and just doing units over 1 over 1 over seconds squared. And this just becomes the square root of seconds squared, which becomes seconds, okay? So one of the things, a lot of people, they don't remember which one goes in the numerator, which one goes in the denominator. If you have a second to work through the units, that can actually be a really helpful thing to do, okay? Because it'll tell you which one goes where. If you did k over m, that would not give you the correct answer. The frequency is just 1 over that. So the frequency is going to be 1 over 2 pi and then square root of k over m instead. So those are how that works. So to talk about a pendulum, I'm just really briefly going to discuss kind of what goes on there. Now, basically what you have, we know that this is basically what a pendulum is. It's kind of going in a partial circle arc between these two, and it normally hangs down from its equilibrium position like so. Now, it turns out pendulums are only simple harmonic if theta is small, so theta being this angle. It's worth noting SHM only for small theta. If you put these things like horizontally and let them drop, then they don't undergo simple harmonic motion. They undergo free fall for a moment until the string catches them, and then they kind of get jerked, and that is definitely not simple. It's kind of sort of a harmonic motion, but there's some other aspects to it. Now, ultimately, if we were to do a free body diagram of this block, what we would have is we would have our force of gravity, and then we'd have our tension force. And it turns out that the net force, if we're going to do this, it's a little too long for force of gravity. It's basically, so this would be F net. It's basically just opposite the direction of the way the thing was displaced, just like it was for the simple harmonic motion. So, or for the mass on a spring. So F net, it is opposite direction of displacement. Now, again, this only works if that tension is maintained, and the bigger you make theta, the sort of less relevant the tension becomes. But basically, this is why this thing undergoes simple harmonic motion. What you have there is you have a force that's pulling it back towards the center, just like you had with the mass on a spring. Okay, so I'm not going to go through the analysis. This one not only requires calculus, but it requires some small angle approximation. So we're not going to do that. But I'll give you the formulas that come out of this. T is equal to 2 pi squared of L over G. F is then equal to 1 over 2 pi squared of G over L. And you can do a similar sort of unit analysis. So length has units of meters. Gravity has units of meters per second squared. And the meters cancel. And just like before, we end up with 1 over seconds squared, which is just equal to the square root of seconds squared, which is just has units of seconds. So you can kind of get these formulas by just looking, just kind of analyzing the units. Okay. Now, the idea behind both of these is that what you have here is you have a force that is, and we'll say a net force that is opposite and proportional to displacement. Okay, so the idea here is that you have a force that wants to pull the thing back towards its equilibrium position, towards its standard position. But that force also gets greater the more you displace it, okay? And this is what we call a linear restoring force. And linear restoring forces, these are the things that give rise to simple harmonic motion. So anything with a linear restoring force is going to give rise to simple harmonic motion, okay? Now, the one thing I did want to talk about is I wanted to talk about damped harmonic motion. And basically what damped harmonic motion is this is SHM with a force to gradually reduce amplitude. Let's say reduce, sometimes it's not gradual. But the idea here is that what you have is you have something that's sort of resisting the simple harmonic motion with the idea that you bring the thing back to its equilibrium position. So a good example of this would be shock absorbers. And the idea is like that's a spring, but it's a very stiff spring. Okay, it doesn't easily it's not easy to transfer energy to it. You have to hit it pretty hard to transfer energy to it, and then it kind of, because it's so stiff, it doesn't really want to convert that back to kinetic energy if it doesn't have to. Okay. And the idea there is that you use the shock absorber in order to transfer a bunch of energy from, like in a car, it transfers some of the work done on the car instead of to the frame where it might break the frame, it transfers that to the spring. But what you also don't want is you don't want the car to be bobbing up and down once it has that energy. So the idea is that that spring dissipates the energy. So you get, a couple of bobs, but then it kind of settles back into its equilibrium position. So that's kind of how a shock absorber works. Now the one thing I did want to talk about is the connection to waves, because waves are what we're going to spend most of our time on. Okay. This week, the remaining 2 lectures we're going to spend on waves. All right. So the idea here is that a wave is the simple definition of wave is it is a disturbance that propagates through a medium. Now, we'll talk more about that in later lectures, but I did want to talk about just how you can connect this to simple harmonic motion through a medium. Okay, so the idea here is that if we have just a simple harmonic oscillator, and I'll just do a mass on a spring. You could do a lot of them, but whoops, do a mass on a spring. So we have the spring, and then we have our mass, and the idea here is this just goes up and down. Okay. Well, the interesting thing is what happens if you take that mass on a spring, and again, you just have it connected there, but this time what you do is you connect something like a string or, something like that. And if you make this mass undergo simple harmonic motion, basically what is going to happen to the string is it's going to rise and fall, but that motion is going to be pushed throughout the string, and you're going to get this wave motion in the string as the mass undergoes simple harmonic motion. So by virtue of the fact that the string is connected to this thing undergoing simple harmonic motion, that up and down, that back and forth motion gets propagated throughout the wave or throughout the medium, which is what we call a wave. Okay, so and we'll talk a lot more about waves, but that's basically what goes on with that. All right. Now there's also another connection to circular motion. So connection to uniform circular motion. And the idea here is that simple harmonic motion, this is uniform circular motion in only one direction. Okay. Now I want to show you what I mean by that. But basically the idea is that uniform circular motion is a two-dimensional is an aspect of two-dimensional motion. If we only consider the x coordinate of circular motion, then that x coordinate is undergoing circular or simple harmonic motion. If we only consider the y coordinate of circular motion, that y coordinate is undergoing simple harmonic motion. And I'll show you what I mean by that as I there's a kind of a cool little video that does this. So open that and bring this to. All right, so okay, sorry about the commercials, but I just want to get to this. So what you can see here is you can see you can see the marker going around in circular motion. But then if all you do is consider it from its side, then basically this yellow cap, you can kind of tell it's getting further away. But if all you can really see is its vertical position here, then it basically is doing the exact same thing as a mass on a spring. And this is side by side. Now here, if you look at just, the horizontal, it's doing the exact same thing as a pendulum. So basically, and you can see that what we're doing here is this thing kind of matches the horizontal position, and this one kind of matches its vertical position. It's not perfect, but it's pretty close. And you can see that basically this thing is just going in a back and forth motion that resembles simple harmonic motion. So that is the connection to simple harmonic motion. We can kind of view circular motion as a form of two-dimensional simple harmonic motion. Now it's not quite accurate to say that because the forces that generate circular motion, they're not the same forces that generate simple harmonic motion, but you do see a pretty similar behavior there. Okay. So that is all that I wanted to talk about for today. So I'm going to go ahead and end the lecture there. Thank you for joining me. I will see you next time.